Hey everyone, welcome to the study package that I give kids when they say they've got an acid-base test the next day and don't know anything. We're going to start with the ultra basics, pun, and work our way up into buffers and titrations. Would you like to come along for the ride? Sure you would. That's why you clicked the video. Step 1, find the pH of a strong acid. Now, your teacher probably gave you a list of strong acids that you had to memorize: HCl, HBr, HI, HNO3, H2SO4, even though only the first H is strong. And then teachers will either give you HClO3 or HClO4. Both of those are strong acids. Strong acids give away one H plus ion every single time you put one of these molecules in solution. What that means is that if you put 0.07 moles per liter of HCl into water, you're going to end up with that same concentration of H plus ions. Now, also confusingly, some teachers will write this as H3O plus. Those are the same thing. Some teachers prefer H plus, some teachers prefer H3O plus. It's because H plus doesn't actually exist in solution on its own. It usually combines with a water to make H3O plus. But because this is the simplified version, lots of teachers prefer it. Anyways, the concentration of H plus, if you put that much HCl into solution, is the same number because it's strong and it gives you H plus in a 1-to-1 ratio. Now, the way you calculate pH, if you already know the concentration of H plus, is with the formula negative log of that concentration. Now, you're probably going to want a calculator for that. Some of you complain that you don't get calculators for it. That's too bad. Try to do it in your head, I guess. You can type the negative sign and log and then type your number. It gives me 1.15. Now, I'm a big fan of using 2 decimals for pHs all the time because that's what pH meters give. You can expect a pH meter to give you a pH of about 1.15 here. Now, remember that anything less than 7 is acidic. In fact, the lower it is, the more acidic that solution is. Anything more than 7 is basic, which is the opposite of acidic. It just means you have so little H plus that we talk about a different ion, OH minus, as being the dominant species instead. This is very acidic. Can you tell? It was a strong acid after all. Now we have a weak acid. I know it was a weak acid because, well, first of all, it's not one of these on the list of strong acids, but also they gave me a Ka. Now, your teacher may give you a pKa. The pKa here would have been 4.87. You can get the Ka, which is the number I think you actually want for your equilibrium calculation, by doing 10 to the power of negative that number. Now, I'm going to do that on my calculator just so you have an idea what it looks like. 10 to the negative 4.87 is 1.35 times 10 to the negative 5. Cool. Now, this is an equilibrium constant, and you might guess by how small it is that this particular reaction favors the reactants. Only a little bit of the acid will break apart to give you H plus. But exactly how much? Well, most teachers are going to ask you to use what's called an ICE table. That's your initial concentrations, your changes, and your equilibrium concentrations. But what happens when you put propionic acid in water? Well, you can call it HA, and if you're going to use this H plus notation, then you just show it breaking up into H plus and separately A minus. Now, those are all aqueous. If your teacher requires you to write states, I'm just going to write a little AQ there. Some teachers will say HA plus H2O makes H3O plus A minus. You can see it's the same thing, but the H plus is attaching to the water. what we have is we're starting with 0.2 moles per liter of the propanoic acid. And we're going to say that we start with none of these, but then the HA breaks apart. How much? We don't know. But we do know that for every one of these that breaks up, keyword that does break up, we're going to gain that many H pluses because there's one inside of each, and we're going to gain that many A minuses. So the equilibrium concentration of HA is 0.2 minus X. The equilibrium concentration of H plus is that same amount X, and the equilibrium concentration of A minus is X as well. Now the reason we did that is because Ka is the equilibrium constant for this reaction. Note the equilibrium arrow. Now, the way that equilibrium constants go, you put your products on top in square brackets because they're concentrations. Now, if there had been a 2 on one of these, you would put a 2 here, as you do for a regular KEQ, but in acid-base chemistry, that's going to be very rare. This HA makes 1 and 1. Now, you also used up some HA to get there. Now, here's where you get to plug in a bunch of numbers. We know the Ka is 1.35 times 10 to the negative 5. You know your H concentration is X. You know your A minus concentration at equilibrium is X. Your equilibrium concentration of HA was 0.2 minus X. Now, you can solve this by multiplying 0.2 minus X on the other side here. You get rid of the denominator here, but you're left with X squared on the right-hand side. It becomes a quadratic equation you can solve. You could use the quadratic formula for that, but boy, do you wish there was an easier way. Well, there is. Some teachers call it the rule of 100, some call it 500, I've even seen up to 1,000. But the point is, you do a test, you ask yourself, is the concentration that I started with divided by Ka more than whatever threshold? Some teachers use as little as 100. So the test we're going to do is with 0.2 moles per liter, that's the initial concentration, divided by the Ka of 1.35 times 10 to the negative 5. Better do that here. 0.2 divided by 1.35 times 10 to the power of negative 5. That gives me 14,814, which is way more than 100 and is even more than 1,000. What that means is that when you start with 0.2 and you take away some small amount X, you're going to end up with about 0.2. It's like if a millionaire drops $1, he's still about a millionaire. And so this can simplify down to just this. Notice how I crossed that out. So the real equation that we have to solve here is, well, 1.35 times 10 to the negative 5 times the denominator of this side. I'm undoing division by 0.2 by multiplying 0.2 on the other side. I get 2.7 times 10 to the negative 6, and that equals x squared. Note x times x is x squared. To get rid of that squared, I square root the other side. So I'll just take that number and square root it. I end up with 1.64 times 10 to the negative 3 as x. Now that's important here because we've decided that x is the equilibrium concentration of H+, which means that's the number that we plug in to this equation. Now I've run out of room here, so I'm going to do it up above. You'll just have to forgive me for that. pH is the negative log of H+. That's the negative log of 1.64 times 10 to the negative 3. Again with the calculator, negative log of the answer. That's 2.78. Cool, that's still acidic, which makes sense because it was an acid, but it's less acidic than this one was. Note that a lower concentration of strong acid was able to give us a more acidic pH than a higher concentration of weak acid. Now that's just the way the math panned out, but overall, there are two ways to calculate pH when you put an acid in water. If it is a strong acid, then the concentration you're given is what you plug into the equation. It's going to be worth like 1 or 2 marks. If it's a weak acid, i.e. not one of these, then you're going to have to do all of this work. Yeah, that's the way it goes. All right, question 3. We're going to be given a base this time. Here, we're asked for the pH of 0.4 mole per liter trimethylamine. You don't have to know the name of that, obviously. You just have to know that it's a base, and we know it's a base in this case because we were given its Kb. Now, again, this means the pKb was 4.20. On your calculator, you might want to actually get this number, 10 to the power of negative 4.2. That gives me 6.31 times 10 to the negative 5. Great. Now, what does Kb represent? Okay, so the answer to that is when you put that base in water, that base is going to steal an H away from water. Note that acids donated their H's to water. This base, Kb, will steal an H away. So what you end up with here is the same formula, CH33N, but you tack an extra H on and a plus, because the extra hydrogen brings a formal charge of +1 with you. And what happens when you remove an H and a plus from this? Well, you're left with a single O and a single H and a minus charge. That's hydroxide OH minus, the hallmark product of a base in water. Now I'm going to refresh your memory again on this ice table. You've got initial, change, and equilibrium concentrations, but what you were given is that you start with 0.4 moles per liter of trimethylamine. You start with none of this and none of this. And by the way, because water is a liquid, the rest of these are aqueous. Because water is a liquid, it does not play a role in this equilibrium. You can cross that out. The rest of this chart should remind you of the last chart we just did. You're going to lose some of this and gain the same amount of each of these. So your equilibrium concentration here is 0.4 minus X, X, and X. Kb is products over reactants, but don't include solids or liquids. That's how equilibrium constants work. What you have here is the concentration of CH33NH plus along with OH minus. Again, that's the one we care about, right? And on bottom, concentration of CH33N on its own. We're given all of these numbers. Kb was given to us, 6.31 times 10 to the negative 5. You made some of this protonated base. That's the conjugate acid, by the way, of the base. We'll cover that in just a moment. It has a concentration of X at equilibrium, and you made just as many OHs out of that as you put in. And likewise, here you have 0.4 minus X. Just compare that to the weak acid stuff we did just before. Oh, it kind of looks almost exactly the same. And likewise, perhaps 0.4 over the Kb, that's concentration divided by K. Perhaps it will be such a large number that we can assume that minus X cancels. Oh, yes, it is. It's about 6,300 way more than 100 or even 1,000. Therefore, 0.4 minus x is still about 0.4. That kind of crosses out. I mean, I'm crossing it out, but it's still an approximation. Okay, let's solve this. You can undo division by 0.4 by multiplying by 0.4. 6.31 times 10 to the negative 5 times 0.4. That gives me 2.524 times 10 to the power of negative 5. That equals x squared, and I can square root both sides to get x on its own. That's 5.02 times 10 to the negative 3. Now that is not my concentration of H+. There is no H+ at play here. It is instead the concentration of OH-. How do you get the pH from an OH- concentration? Well, I'm going to show you my favorite way. It's by calculating the pOH, which is the same formula, but you use OH- instead of H+. And then you can calculate pH by doing 14 minus that number. Now, this equation only works at room temperature. We've not been told that this is at any temperature other than room temperature, so let's just roll with it. That 14 is, by the way, pKw on your formula sheet, if you're given one. Anyways, for me, it's negative log of 5.02 times 10 to the negative 3. When I do that on the calculator, it gives me a syntax error. Negative log of 5.02 times 10 to the negative 3. Gives me 2.30. Now that might seem acidic to you, but it's not the pH. The pH is actually 14 minus that, so it turns out to be 11.7. Ah, that's quite basic because it's more than 7. And that makes sense because we put a base, not an acid, into water. Very nice. Would you like some more? Here is sodium acetate. This is a salt. This is made when you react acetic acid or vinegar with sodium hydroxide. The H from the acid and the OH- from the base react together, and it leaves you with this. Now that water is neutral, so basically doesn't even matter. But what's the effect of putting these in water? Well, I can tell you that alkali metals like Li+, Na+, K+, etc., we generally assume that they do not have an effect on pH. If your teacher happened to mention that Li+ is acidic, there's a very specific and obscure reason for that. Go with that if you've heard of it. Most teachers will assume it has no effect on pH. And so you can ignore those ions when you're doing pH calculations. What's attached to them might have an effect. Now, if this counter ion had have been Cl-, Br-, I-, NO3-, any of the anions that correspond to these strong acids, then they also would have had no effect. Because they, in their protonated form, are strong, that acid would always break apart to give you this, and thus this is not strong enough to steal that H back. This acetate is not on that list, and thus it does have an effect. But it is the conjugate base of ethanoic acid or acetic acid or vinegar, CH3COOH, which you've almost certainly seen in your travels. Note we are being given the Ka for that acid even though this is its conjugate base. I'm going to show you what that means. its conjugate base in water will have the effect of stealing the H back. Acids break apart to give you H+. This is missing its H+, and so can steal it back. CH3COO- having stolen an H back away from water would give you that acid, ethanoic acid CH3COOH, but losing the H+ from this leaves you with OH-. That's why putting the conjugate base in water gives you a basic solution. It's giving you OH-, obviously not H+. Now, the reaction that I've just written, because it is for a conjugate base stealing an H away from water, actually corresponds to Kb. How do you get Kb from Ka? Well, I'll tell you. You can get either one of them from the other by taking what they call Kw and dividing it by the other. Here, Kb is Kw divided by Ka. That is always 10 to the power of negative 14, or 1 times 10 to the power of negative 14, divided by whatever the Ka of the acid was. Here it's 10 to the negative 4.76. My calculator is definitely going to give me that in a funny way. Let's see. Now, I don't want to confuse you here. This is 10 to the negative 14, so I need you to type just 10 to the power of negative 14. Notice on the calculator it says 1 times 10 to the negative 14. That's because in scientific notation, 1 times 10 to the something is just this amount. 1 times anything gives itself. I'm overcomplicating it. Just type this into your calculator exactly. Divided by 10 to the power of negative 4.76. This gives me 5.75 times 10 to the power of negative 10. That's a small number. I know that because it's a deeply negative power on the 10 here in scientific notation. That implies to me that this is a weak acid, but this, I think, is an even weaker conjugate base. Okay, let's not lose sight of what we're doing. We were given 0.3 moles per liter of this. H2O can be ignored, and we start with none of these. The change here is that we're losing some of this and gaining commensurate amounts of this. So it's 0.3 minus x, and x, and x. Have you seen that this is the third time we've gotten an ice table like this? Are you bored yet? I hope not, because chemistry is exciting. And the Kb expression is products over reactants. This is a product. It's written on the right-hand side. This is a product. It's written on the right-hand side of the equilibrium arrow. That gets ignored, and this goes in the denominator. It's probably also not a surprise. So 5.75 times 10 to the negative 10 is x times x all over 0.3 minus x. Again, look how similar that is to what we had in question 2 and 3. Now this Kb is so small. I know that x is going to be almost useless. We even found that that you could cancel the x out when the K was 10 to the power of negative 5. Now it's negative 10 and you're going to try to pretend it matters? Nah, you're getting rid of that. Prove it to yourself if your teacher demands that. You're going to take this number and times it by 0.3, and then you're going to square root it to get x. That gives me an x of 1.31 times 10 to the negative 5. And according to my ice table, x is the concentration of OH-. All right, let's get it. That means the POH is the negative log of that concentration. La la la. Negative log of that 4.88. And don't forget, that's pOH. So the pH is 14 minus that. 14 minus that answer, 9.12. Still basic, but not particularly basic. It's only a couple units, or well, I guess orders of magnitude above neutral, or 7. There you go. Note that there was no H plus or OH minus added directly to solution here. It was the conjugate base stealing H away from water that gave you OH minus. Okay, my last pH calculation question has NH4NO3 dissolving in it. Now, we've already agreed that NO3 minus, as the conjugate base of a strong acid, HNO3, has no effect. But NH4 plus is weakly acidic. Now, I know that because I've been in this game for a while, but it's clearly got an extra H and a plus charge that it might be able to give away. And another hint is that ammonia, NH3, is probably a base that you're given the Kb of. Note that ammonia, having stolen an H away from water, would have formed NH4. One more H and an extra plus charge. So this is the conjugate acid of ammonia, which means that this is probably weakly acidic. What would happen if you put NH4 plus into water? Now I'm actually going to show you what happens by adding the water in there. It, as an acid, gives an H plus away. You would form NH3, and that extra H plus would attach to water. You get H3O with a plus charge. I warned you, some teachers will use H3O plus instead of H plus to represent acids. I'm going to do this same reaction again the other way, showing NH4 plus as an acid, alone, simply breaking apart into NH3 and H plus. See how similar these are? Something either gives an H away to water to make H3O plus, or magically breaks apart to give you H plus. This second one is not how it works in the real world. In the real world, you are donating H to water, but look how much simpler that is. Do you like it? I do. Doesn't matter though. What matters is how you prefer it, or rather, how your teacher prefers it. Am I right? You're starting with 0.7 moles per liter of this. Water gets ignored no matter what. You're starting with none of these. You're losing some, you're gaining some. You end up with your starting concentration minus X here, and X here. Beauty. Now, this is your conjugate acid breaking apart to give you H+, which means you need the Ka. Oh boy, how do you get Ka from Kb? The same way we converted Kb to Ka. 10 to the negative 14 divided by whatever number they gave you here. For me, it's 10 to the negative 4.75. 10 to the power of negative 14 divided by 10 to the power of negative 4.75. I got 5.62 times 10 to the negative 10. Oh, another number in the 10 to the negative 10s. Whatever, let's just roll with it. The Ka is the equilibrium concentration of NH3 times either H plus or H3O plus, and your equilibrium concentration of NH4 plus, the conjugate acid that you added to solution directly to make this solution acidic. 5.62 times 10 to the negative 10 is X times X all over 0.7 minus X. 10 to the negative 10 is such a small amount that that minus X will be absolutely useless relative to 0.7. So 5.62 times 10 to the negative 10 times 0.7. That gives me 3.94 times 10 to the negative 10. And then I square root both sides. My x is 1.98 times 10 to the negative 5. And that is my H plus concentration. See? Thus, I can calculate pH directly by doing the negative log of that H plus concentration. That's the negative log of 1.98 times 10 to the negative 5. I just want to point out how small that number is relative to the 0.7. This truly is a case of like, if 0.7 represents a millionaire, you're dropping $1 or like $5. You're still basically a millionaire. There was no real importance to this 0.7 of the 0.0000 something extra that you were going to lose. It's still about 0.7. Anyways, you take the negative log of the answer, and I get a pH of 4.70. Acidic, which makes sense because we added the conjugate acid of ammonia. Very nice. Now I've been throwing around Ka and Kb as though we all know what they are. Let me just tell you that the higher a Ka is, the more acidic that acid is. Higher Ka equals stronger acid. And by the way, a higher Kb corresponds to a stronger base. Now your teacher might end up asking you about pKa's, and P, as you might have been able to tell from every question before now, is the negative log of Ka. But what that actually means is that a higher Ka actually gives you a lower pKa. It's because of the negative. The higher the Ka is, taking the log of it, it doesn't affect the order. Like it's a monotonic. I don't know. I don't want to confuse you with the math. A higher Ka gives you a stronger acid, and a lower pKa also corresponds to a stronger acid. It's simply because of this negative here. You're flipping the difference between higher and lower, okay? What that means is that the lower pKa is the strongest acid here. Of these four, methanoic, ethanoic, propanoic, and whatever this is, you just look at the pKa's. The lower one is the stronger acid. If they'd have given you Ka's, you would have looked for the higher number. Correspondingly, of these four, this is the weakest acid because it has the higher pKa. And you can play that game here as well. The strongest base corresponds to the lowest pKb. Well, I spelled it wrong, but you get the idea. And I'll even write it here. A lower pKb also means a stronger base. It's methylamine here. And obviously, the higher the pKb, the weaker the acid. So that means phenylamine is the weakest of these four. Just throwing it out there in case you have to rank your acids. All right. How about conjugate acids and bases? I have touched on these as well, but I want you to be ready for these 1-mark questions that teachers like. How do you get the conjugate acid of HSO4-? Well, you can treat this as a base, and the conjugate acid of it has an extra H plus on it. So the answer here is add an extra H, that gives you H2. All the other atoms stay the same, that's SO4. And you're going to add 1 to the charge. This charge was -1. Adding 1 to that gives you 0, and so I will not write a charge there. It is neutral. The conjugate base of that thing is what you get when you take away an H and a plus charge. So 1H is here. We're going to write it without. You still have your SO4, and you're going to take 1 away from this charge. That's -1. When you take away another 1, you get -2. That's the sulfate ion. H2SO4 is the conjugate acid of HSO4 minus. SO4 2 minus is the conjugate base of it. I just want to point out that HSO4 minus can both gain an H and lose an H. Lots of teachers will call that amphoteric or amphiprotic. Now, there's actually a difference between these two. Amphiprotic is specifically for the chemicals that have an H, that can either accept a new one or give that extra one away. Amphoteric is for substances that can be acidic or basic, whether or not they have an H, but some teachers use them interchangeably. I want you to be ready for it. How do you get the conjugate base of this? Well, I want you to remember that COOH is the ending of a carboxylic acid molecule. So that's the H you're going to lose. I don't want you losing the H's off of the carbon chain here. The hydrogens connected to carbons are not likely to fall off the molecule the same way these H's can. So the correct answer here is CH3, CH26. Leave all of that intact. COO, take that H away because you're making the conjugate base. And take away a +1. We're starting at neutral, so taking away a plus gives us a minus charge. That's your conjugate base. The conjugate acid of a chemical has an extra H added on to it. If you're into Lewis structures, I want you to remember that that H plus ion is going to attach to wherever the lone pair of electrons is on the Lewis structure. Carbons and hydrogens almost never have lone pairs of electrons on them, which means that the ideal place for you to write this extra H is on the N. Nitrogen does often have a lone pair in its Lewis structure, so add your H onto N. And don't forget to notch the charge up by 1. From 0, it becomes +1. Very nice. The conjugate acid of O2-, well, acid means you add an H. Well, conjugate acid means you add an H relative to this. So, give yourself an extra H and make this go up by 1. It's currently -2, and so just take it to -1. What you'll note, by the way, is that charges can be written in either order, -2 or 2-. Both of those are acceptable when you're doing the charge on a particle. Now, here, I actually am not giving you a choice about which H to remove. It has to be one that's attached to carbon. You're ripping an H away, and it's becoming its conjugate base. So, give yourself that H, that C. You still have your triple bond. You have that C, but you'll remove an H because that's what conjugate base represents. And don't forget to take away the extra plus charge, so you're left with a minus charge. I know that looks weird, but they're testing you to see if you know what a conjugate base is. It's the same thing without one of the H's. Now, the conjugate base of this particle is what you get when you remove an H. Note, I told you that COOH is what you get when it's a carboxylic acid, and it's that H that's likely to come off. So when you're getting the conjugate base, I want you to remove that one, CH2COO-. If you were going to add an H as you need to get the conjugate acid, you have to add it to a atom that has a lone pair. Now, you might already recognize that N makes for a popular base. If I didn't throw away my old ones here, I don't know, this one will do. You see these lists of bases, and they all have nitrogen in it. That's because N loves accepting H's. So I'm going to ask you to add the extra H of the conjugate acid onto that N. Make it H3N, CH2COOH. Now that has an extra H relative to what it did. Don't forget to notch the charge up by 1. That charge is not on this H. It's more accurately actually on the N. But by convention, we write the charge at the end. For those of you who are into biology, I just want to emphasize that I gave you this because this is an amino acid. Does that ring a bell from biology? It probably should, but I didn't take any, so I don't know. You probably know more than me about that. You want to talk about buffers? Because I do. Which of these solutions make a buffer? Well, let's talk about what even makes a buffer in the first place. First of all, you need to have a weak acid or base dissolved in water and some of its conjugate as well. That's why I'm doing this question right after we identified conjugate acid-base pairs. Buffers resist changes in pH. We'll talk about that more in the titration section. But the reason it's able to do that is that you'll have some of the weak acid in solution, so that will help to neutralize additions of base if you make any. And you're going to have some of its conjugate base in solution as well. That would help to neutralize any acid you might have added. You can't have a buffer if you don't have a weak acid and its conjugate base, which is the same way of saying a weak base and its conjugate acid. So the question is, do we even have a buffer solution here? When you mix 1 mole of HCl with 2 moles of NaOH, the first thing I want you to see here is that that's a strong acid and that's a strong base. Now, I don't think I've told you exactly what makes something a strong base. Strong bases are generally hydroxides at all. So the common ones are LiOH, NaOH, and KOH. Some teachers include CaOH2. What's the other one? Ba, or barium hydroxide, BaOH2. Note that these are all ionic compounds with hydroxide ions. These are the things that when they dissolve in water, you get OH- made directly. The same way, for strong acids, you make H+ directly. Cool. So before I even do a little math here, that's a strong acid, that's a strong base. There's nothing weak here at all. So, how is it going to be a buffer? The answer is it's not. You can't make a buffer out of strong acids and bases together. You need something weak. I want to point out here that HCl and NaOH, when they react together, the H and the OH neutralize each other to make water, and you get NaCl, a salt, as well. It's kind of like a double displacement reaction. If you're reacting 1 mole of HCl with 2 moles of NaOH, you're going to use up all the HCl, have NaOH left over, and so the real thing that's controlling the pH of this solution is the leftover strong base. The water that you made certainly won't affect pH. It's water. And NaCl does not affect pH because Na is the counter ion to hydroxide in this strong base, and Cl is the conjugate of HCl, which was strong. And strong things have conjugates or counter ions that are entirely impotent and powerless. Anyways, we have more HCl mixed with more NaOH. Strong acid, strong base? Heck no, you won't have a buffer. And HCl and NH3. Oh, here we go. Now we have something that's weak. HCl plus NH3. When those react together, the H from the acid will go to the base, right? Acids give away H, bases accept H. So you end up with NH4 plus and Cl minus. Now this is a weak base and this is its conjugate acid. You can think of this as a weak acid and this is its conjugate base. That's the same thing. But let's just see if we have some of that weak acid and its conjugate base in solution at the end of this. 1 mole of HCl and 2 moles of NH3. When they react, you're going to use up the HCl, you're going to use up the same amount of NH3, and you're going to make that same amount of each of these. So because we added more of the weak base than conjugate acid, strong acid, it means we do have some conjugate base left over, and we formed some of its conjugate acid in solution. The answer here is yes, because you'll have NH3 left over, you had more of it to start after all, and you made its conjugate acid forcefully by reacting it with strong acid. Very nice. Here, though, you're adding the same amount of both, which means that when you use up all the HCl, you've converted all of this to NH4 plus. That means you'll have none of this left over, and so you do not have a buffer solution. In E, we have NH3, and we are directly adding its conjugate acid, NH4 plus, as a salt, NH4Cl, but that's going to dissolve, dissociate, and give me NH4 plus, its conjugate acid. This is a classic way to make a buffer. You add weak base and its conjugate acid directly to solution at the same time. There's generally 2 ways to make buffers, by the way. You can either add base and conjugate acid, or acid and conjugate base both directly to a solution, like we're doing here, or you can start with a weak base or acid and create some of its conjugate by forcefully reacting it with something else in solution. What else do we have here? Here we have acetic acid written in a funky way. This is actually just another way of writing CH3COOH. I'm like, why do they do that? I don't know. They just do sometimes. Look, there's 2 C's. There's your H3. There's your O2. And there's your extra H. Like, they're technically the same thing because they have the same number of atoms. They're just written terribly. What can you do? That's acetic acid, a weak acid. And its conjugate base added directly. Note that this C2H3O2 is the same as this formula, but without the leading H. When this dissociates, the Na plus comes off. You end up with a -1 charge here. Does that look like a conjugate base to you? It should. This is a buffer because you're adding acid and its conjugate base directly. How about this one? You're adding an acid and its conjugate base directly, but it was not weak. It has to be a weak acid or base and its conjugate. So even though this one looks so similar to the one above it, because nitric acid is strong, it cannot form a buffer with its conjugate base. Whew. Here we have H2SO3. That is a weak acid reacting with KOH, a strong base. Let's just go take a look. We got H2SO3. We got KOH. When they react together, now I'm going to react just one of these H's away, just to simplify things. That H and that OH pair together to give you H2O. And that K goes with the rest of this molecule, KHSO3. Sure, that KHSO3 could react another time to give you K2SO3. You can consider that if you'd like. But what really matters here is that you're adding the same volume of each, but the concentration of the strong base is half of the weak acid. If I was to calculate the number of moles here, I'd have to do concentration times volume, but I'd convert my volume to liters. I convert milliliters to liters by dividing by 1,000. I get 0.01. Moles per liter times liters gives me 0.001 moles of that. Concentration times volume gives me 0.0005 of that. I'm going to run into this first. I have none of it left. That's promising that I got rid of all my strong base. I'm left with half of this amount, so I still have some of my weak acid in solution. I really don't care about water, and I'm forming some of this. What I'm doing here isn't exactly an ice table, because ice tables are for equilibrium, and I'm actually doing a chemical reaction here, but it might have reminded you of it. So in the end, because I used up my strong base, I have weak acid and its conjugate base in solution. I added less strong base than I started with of weak acid. Therefore, some of the weak acid gets converted into its conjugate base, and it's a buffer. Great. Now, this is a trick question as well. H2SO4, along with its conjugate base, sounds like a buffer, but H2SO4 is a strong acid. Oh, that's supposed to be an N. For no, it's not, for the same reason that this one isn't. But you may have remembered what I said at the very beginning. Only the first H of H2SO4 acts like that. And by the way, when I say like that, I mean like a strong acid, giving away all of its H to become its conjugate base. The second H of sulfuric acid is not strong. Like, it's pretty acidic, but it's not so strong that we say 100% of it dissociates to give you H+. So this is a buffer because you have a weak acid, HSO4-, and its conjugate base, SO42-, in solution at the same time. You've added them both directly here. Repeat. Adding a strong acid and its conjugate base does not form a buffer. You need a weak acid and its conjugate base to form a buffer. Great. Let's talk about the pH of buffer solutions. Now, before we get too excited, I want to remind you that there is a shortcut for the pH of some buffer solutions. It's called the Henderson-Hasselbalch equation. And it is the pH of the buffer is the pKa of the weak acid plus the log of the base concentration over the acid concentration. And the dirty trick that you're allowed to use is that these don't have to be concentrations, they can also be numbers of moles. Henderson-Hasselbalch equation. What is the pH of 100 milliliters if it contains 0.2 moles per liter of a weak acid and 0.15 moles per liter of its conjugate base? I know that because it's HF, not on the list of strong acids, even though HCl, HBr, and HI, all the other hydrogen halides, are strong acids, not HF. And its conjugate base, when NaF breaks apart or dissociates in solution, you get Na+, but no one cares, and you get F-. Everyone cares about that because it's the conjugate of a weak acid. So the pH of this buffer is whatever the pKa of HF is plus the log of the concentration of conjugate base over the concentration of weak acid. Now, how do you get pKa from Ka? I already told you, but I'll tell you again. It's the negative log of the Ka itself. That's the negative log of 6.6 times 10 to the minus 4. And then I'm going to add the log of base concentration, which was given as 0.15, over acid concentration, which was given as 0.2. Now you could probably do all of that on your calculator all at once, but I'll do it piece by piece. Negative log of 6.6 times 10 to the negative 4. That gives me 3.18. And then I'm going to add the log of 0.15 divided by 0.2. That's negative 0.12. Adding a negative is like subtracting, so I end up with 0 or 3.06. Cool. Now, 3.18 is the pH that it would have been if I added the same amount of acid and conjugate base. But because I added a little bit more acid, I ended up with a slightly more acidic pH. Get it? Numbers are beautiful, just like you are. Now, what if I use HClO, hypochlorous acid, and I get rid of some of it with KOH? Well, I'm going to show you what happens directly here. HClO, the acid, will react with the strong base KOH. The acid, H, reacts with the base OH to give you water. That's why it's called neutralization after all. And you end up with the salt left over, potassium hypochlorite, or K+, along with ClO- as its counter ion. But what really matters here is which one of these we run out of first. I'm going to calculate the number of moles here. It's 0.3 moles per liter times, now I'm going to times it by milliliters to show you another trick. Milliliters times moles per liter will directly give you something called millimoles. The milli is preserved. It's basically like moles, except you've times by 1,000 to get a smaller unit. The unit itself you can call mmol, millimoles. If you want to convert that to liters by dividing by 1,000, then timesing by 0.3, you'll get 0.015, and that's totally cool. You do you. 50 milliliters times 0.1 gives me 5 millimoles of KOH. Which of them runs out first when they react together? Well, the KOH gets used up. You're left with 10 millimoles of this. You form some water, 5 millimoles of it to be exact, although no one cares. And you get 5 millimoles of this as well. Notice we went down by 5 for each of the reactants and up by 5 for each of the products. What are we left with in solution? Well, we are left with weak acid, some of it, and we have some of its conjugate base here in solution. Now K has a +1 charge, ClO- has a -1 charge. They combine to form this ionic compound if it was solid, but it's dissolved in water. So you just have ClO- dissolved in water. Look at that, weak acid and its conjugate base. Buffer, you know what that means to me? Henderson-Hasselbalch equation, pH equals pKa plus the log of base over acid. All right, I was given the Ka of the acid here, so that's negative log of that number for pKa. If you were given the Kb of the conjugate base, then you could just convert it to a Ka on your own. Remember, it's 10 to the negative 14 divided by this to turn it into the other version of K, like Kb in this case. It would have been Ka if this had been Kb. Whatever. pKa is the negative log of the Ka, and then I'll add the log of base over acid. Now the formula I wrote for you before had these as concentrations, but the trick is you can use quantity, number of moles instead. Base is 5 millimoles. Conjugate acid is 10 millimoles remaining. Now, that isn't exactly the concentration that's going to be remaining. Equilibrium will occur with these as your starting amounts. But for the Henderson-Hasselbalch equation, it already builds the equilibrium in with the pKa, so you don't have to worry about it. Negative log of 2.9 times 10 to the negative 8 gives me a pH of 7.54 plus, and then I do the log of this, log of 5 over 10. That's negative 0.30. When I do 7.54 plus a negative, I get 7.24. The pH of this solution is slightly basic, more than 7. I guess we've added enough strong acid to make enough conjugate base that it plays a stronger role on pH than the weak acid does. It's just the way it fell apart here. One more buffer question. This one, we start with 0.5 moles of methylamine, and we're going to add some strong acid to it. Just want to point out methylamine was on this list of bases. You can also know that it's a base because it says amine. That means nitrogen, and nitrogen loves stealing H away from other things. So CH3NH2, the base, will react with some HBr. What will it give us? Bases take H away from acids. So this is CH3NH3 with an extra plus charge. And the Br minus is now on its own, robbed of its H plus. Of course it's robbed of its H plus. HBr is a strong acid, and the H just falls right off of it. We're going to start with 0.5 moles of this. We're reacting with 0.15 moles of HBr. That means we're going to use all of that up. We're going to take 0.15 away from this and be left with 0.35 moles of it. And we're forming 0.15 moles of each of these things. I do not care about the bromide that was made. Bromide does not have an effect on pH because it's the conjugate of a strong acid. But what we do have here is some weak base and its conjugate acid in solution. Wow. Now, some teachers will give you a different version of the Henderson-Hasselbalch equation based off of Kb. But I want to show you that you can use the same equation that you've always used, pKa plus the log of base over acid, in both cases. Now, I expect this solution to be basic because we have lots of this base remaining, certainly more base than we created of conjugate acid. And this Kb is pretty high relative to some of the other numbers we've seen, which leads me to believe it's not so weak of a base that it can be easily overpowered. Anyways, how am I going to get pKa from Kb? Oh, you already know the answer to that. I can get Ka by doing 10 to the negative 14 divided by that number. And then I can get pKa by doing the negative log of it. 10 to the power of negative 14 divided by 4.4 times 10 to the negative 4. Gives me 2.27 times 10 to the negative 11. And so the pKa is the negative log of that number, 10.64. Note that that, as a starting point, definitely implies that we're going to have a basic pH here. That's way above 7. But let's see this through. We have to add the log of base. The base concentration is 0.35. The acid concentration is 0.15. They're not concentrations. It's supposed to be concentration in this formula, but again, I'm using the shortcut where I can use raw numbers of moles instead of actual concentration. Just saves me from having to divide my volume twice to get concentration, and then those are going to cancel each other out anyways. 10.64 plus log of 0.35 divided by 0.15, that's 0.37. When I add those two together, I get 11.01, a very basic pH, as I expected. Great. Even though I use the Henderson-Hasselbalch equation that looks like it's meant for acids, it still worked here because I converted the Kb for the base into pKa properly. Wow, what a time to be alive. You want to talk about titrations? Well, I'm sure you do because you want to get an A on this test, don't you? Oh no, I lost question 12. Label this titration curve. This is just in case you haven't seen a titration curve in quite a while. The way that these work is that you're adding some of something. I guess, let me be clear. The y-axis on a titration curve is always pH. And then somewhere along here, we have a pH of 7, which is neutral. Anything below 7 is an acid. Anything above 7 is a base. You can see here that we're starting with an acid, and then we're becoming more and more basic. See how it's rising? The pH is going up as we go from left to right. That must be because we are adding a base. What that means is that the x-axis here is the volume of base added, usually in milliliters. Sometimes you'll see moles of base added. Really depends on who created the graph, I guess. Okay, so let me point a couple extra things out here. The way the titrations work is you start with either a weak or strong acid, and then you add weak or strong acid to the mixture to change the pH. Eventually you'll get through the neutralization point and end up somewhere else. Now, if you form a buffer, you'll end up with a flat section in the first half of the titration curve. What did we say before? A buffer resists changes in pH. So if you start with a weak acid, then you're going to quickly rise in pH for just a short time until you have formed some of the conjugate base in solution. But then at that point, you have some conjugate acid, or weak acid, and its conjugate base in solution at the same time. So instead of your base that you're adding, all you're really doing is converting weak acid into its conjugate base, and you're not actually adding OH minus. You're just doing some work with it. That causes it to flatten here. And so if you end up with an S-shaped curve in the first half, and I'm talking about something that looks like this, it rises, then flattens, and I did have it here, then this is called the buffer region. The halfway point to your vertical line gets a special name. It is called your buffer point. It is when you have the exact same amount of weak acid as conjugate base in solution at the same time. According to the Henderson-Hasselbalch equation, if these two are equal, then base divided by acid is 1, because anything divided by itself is 1. And then when you take the log of 1, you get 0, so the pH is equal to the pKa. I lost question 12 here. That's too bad. But we wanted you to identify the pKa of the acid. I guarantee you, whatever the pH is of this buffer point, the point that represents your pH halfway to the vertical section of your graph, I guarantee you that is the pKa of your acid. Always when you're starting with a weak acid and titrating it. So I've answered question 12 here. Wherever the halfway point, like, and by that I mean, I don't know, maybe this is like 20 milliliters here for this vertical line, then find 10 here. Whatever your pH is happens to be the pKa of the acid. Then you can just look that up on a chart somewhere and identify your acid based on that. I believe the answer to 12B was acetic acid according to the charts that I gave you earlier in the package. Here we are. I want to point out that this point here can be one of two things. It really depends on how your teacher likes to graph these. I think, personally, that the equivalence point is going to be somewhere around here. Actually, I should be above 7. I'll label that as the equivalence point, whatever, slightly basic. It represents the point when you've added as much base, maybe it's NaOH, as you started with of weak acid. I don't know, HF. When you've added the same number of both of these, you've made all of your OHs into water along with these H's, and you're left only with the salt that's formed when the neutralization reaction occurs. So the pH at the equivalence point is based only on the pH of this salt in water. That is different from what teachers call the end point of the titration. If you've done a titration in class, you'll remember doing drip, 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 drip. And then all of a sudden, a couple drips turned your solution bright pink if you used phenolphthalein. There's no way you were able to stop it at the very first sign of pink. And what I mean by that is the very first molecule of pink that forms of phenolphthalein. You always overshoot it by at least half or 1 drop. So you end up a little bit higher in pH than the actual equivalence point. That's why, realistically, it's ideal if you do this with a pH meter that's immersed in solution. So you can drip, 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 drip. And then even if you overshoot the equivalence point, the computer will figure out where the actual equivalence point was for you. The end point is different because it's where you actually finish your titration. And the equivalence point is where you've added exactly the same number of moles of acid and base. Get it? Equivalence point, equal amounts. There you go. So the last thing I want to point out here is that you are starting with a weak acid, and I know that because you are below 7 to start and you have this little S-shaped thing. That's how I know it's weak. By the way, if it was strong, it would just rise up with a straight line and then do its thing like that. And I'm going to guess that we are adding a strong base here simply because we have such a violent rise from like pH 4 to pH 10 in just a couple drops. A weak acid, weak base titration will generally have a more gradual slope, and it's tougher to see where the equivalence point is. Titration of weak acid with strong base. Yeah, that's it. Just like HF and NaOH, similar to the graph that I would have given you in question 12 here. I'm so sorry that this video includes a question 12 that does not have the graph printed the same way. Google Docs lied to me about how that was going to print. But go find the point on the S part of the curve that is halfway to equivalence. Find the vertical portion of this curve, draw a dotted line for yourself, see what the volume is. Then go to the volume that is half that amount, see what the pH was at that volume. That's the pKa. Then you can look it up in the chart. Where did my chart go? I don't know, I keep throwing my papers all over the place. You can identify the acid based off of that. The last question here in question 12 is, what would be a good indicator for this titration? What you'll notice is that this aggressive vertical portion means that the most violent change in pH happens here, which is slightly above 7. So what you want is an indicator that works in the pH range where your equivalence point is expected to be. Now, when I'm mixing strong base with weak acid, when I've added the same amount of both, I'm expecting the base to win because the base is stronger than the acid. Same number of both, the stronger one's going to win. So what I want is an indicator that works at a slightly basic pH, and that's the same here. I think you'll find that phenolphthalein is the most common one that you can use when your equivalence point is a slightly basic pH. Your teacher would have to give you a list of the indicators they want you to know about to ask you this. The reason is there's like 100,000 different indicators you could use. They can't. They're just going to give you a list. So you're looking for one whose pKa, or the pKa at which it changes, is the pH when the equivalence point occurs. If it's slightly basic, use phenolphthalein. If it's slightly acidic, I forget. I think it's methyl orange that teachers like using. Okay, and we're going to do some titration calculations as well. In the titration of 25 milliliters of 0.1 molar HCl with some 0.1 molar NaOH, what is the pH after 15 milliliters of that NaOH has been added? Okay, there's a lot going on here, but let me show you what really matters. The number of moles of HCl that you're starting with is concentration times volume. I'm not going to do anything fancy here. I'm just going to use the concentration in moles per liter times the volume in liters. I'm dividing it by 1,000 to get liters from milliliters. It means that I start with this many moles of HCl. How many moles of NaOH will I have added? Well, I was given the concentration of the NaOH, that's 0.1 moles per liter, and I'm given the volume of NaOH as well. That's 0.015 liters, which means I've added 0.0015 moles of NaOH. What happens when I react this strong acid with this strong base? Well, let's go find out. Acid plus base equals salt plus water is the general rule. Note, H and OH made H2O, Na and Cl made NaCl, a salt. Now again, I'm not doing an ice table. I'm actually just figuring out which one of these runs out first. I'm starting with that many moles of HCl. I'm starting out with this many moles of NaOH, and I'm using them up in a 1-to-1 ratio. So the smaller one is the one I'm going to run out of, and I'm going to go down by that amount here as well. When I subtract it away, it leaves me with 0.001 moles of HCl left over. I'm going to gain that amount of NaCl. By the way, no one cares because Na plus is powerless in water and Cl minus is powerless in water because they're the conjugate and counterion for strong things. And I'm forming that many moles of water, but we definitely don't care about that because It's just water, it's neutral. So the question I have for you here is, what is left over at the end of the mixing of these two that actually controls pH? This certainly doesn't affect pH. Water doesn't affect pH, except for the fact that you're diluting your solution a tiny amount. HCl, the strong acid, that affects pH. We all know by now that pH is the negative log of the H plus concentration, and for a strong acid, it's the concentration of HCl. But we don't have the concentration yet. The concentration is moles divided by volume. We do know the number of moles that's remaining. It was the difference between moles of HCl that we started with and how much NaOH we used up in reaction with it. But watch out for your volume. You started with 25 milliliters of HCl and you added 15 milliliters of NaOH. That gives you 40 milliliters total. And so you need to use that total volume for V in this calculation. Let's take a quick look here. 0.001 moles divided by 0.04 liters gives me a concentration of HCl of 0.025. It is the only thing in this solution after reaction that affects pH. So it, as a strong acid, gives us that concentration of H+. Go do it on your calculator. Negative log of that answer gives me a pH of 1.60. Now, we've actually already titrated away 3/5 of the HCl, and yet we still have a very acidic pH. If I take the negative log of 0.1 here, I'm actually starting at a pH of 1, and then I'm adding NaOH, so my pH is rising. If I was to draw a curve here, I'd have to start at a pH of 1. That's the pH of this concentration of HCl. Hello, question 1 of the package. And then I'm slowly rising, and I'm getting to 1.6 by the time I'm 3/5 of the way to equivalence, which means the graph is probably going to look something like this. Oh, look, it's a titration curve, just like the question we saw before. Please note that because it's strong acid, strong base, I don't have that rise and flatten that you get when you have a buffer solution. You can't get a buffer solution with strong acid, strong base. Instead, it's just a gradual rise and then a violent rise upwards once you get to equivalence. Very nice. More. When titrating 20 milliliters of 0.12 HCN, that is a weak acid because it is not on the list of strong acids with some NaOH. You've reached equivalence when you've added 30 milliliters of NaOH. Oh, they didn't have to tell us that, did they? We could have figured that out for ourselves. Concentration times volume of HCN, number of moles, equals concentration times volume of NaOH, numbers of moles, and they're required in a 1-to-1 ratio. We could have calculated that ourselves, but hey, once we've added 30 milliliters of NaOH, we want to know the pH. Ooh, pH at equivalence. I like that. What do we have at that point? Well, let's go find out. The number of moles of HCN is concentration times volume, 0.12 moles per liter, 0.02 liters. I feel like I should be able to do that in my head, and yet I don't. 0.0024 moles of HCN. They told us it was equivalence, and so that means the moles of NaOH that I added was the same amount, but it should be whatever you get when you multiply that concentration by that volume. P.S. If you needed that volume, you just take this number of moles and divide it by the concentration to get volume. Anyways, HCN, a weak acid, will react with NaOH to give you H and OH make water, Na and Cn make NaCN. Get it? Acid plus base equals salt plus water. You're starting with 0.0024 moles of this, 0.0024 moles of that. You're going to take away that same amount from both, and you're left with none. Oh, right, it's the equivalence point. You're using the same number of moles of each. And so you're going to make that number of moles of water, no one cares, and you're going to make that number of moles of conjugate base. Ah, here we go. The Na+ that is part of this salt is powerless. It's the counter ion for a strong base, and so doesn't do anything. Cn- is the conjugate base of a weak acid, so it does have an effect on pH. This is what matters when we're calculating the pH at equivalence. All right, this should remind you of, I think it's question 5, where we had sodium acetate in water, except here it's sodium cyanide. We're given the Ka for HCN, but that's not what we are starting with. We are starting with Cn-, which reacts with water. And I know that that's kind of what we have here, but I want to point out the acid and base are neutralizing each other to make Cn-. Now the Cn- is alone in solution. What does it do? It can steal H's away from water to form HCN and OH- in the process. Now that's an equilibrium because it's a weak base. Well, it is the conjugate of a weak acid and therefore is a weak base reacting with water. The initial concentration of it, damn, I don't know the answer to that. Concentration is moles over volume. 0.0024 moles divided by total volume 50 milliliters, aka 0.05 liters. That calls for a calculator. It's 0.048 moles per liter. That's the number we need in our ice table. We are starting with that concentration of HCN. No one cares about the water. We're not starting with any HCN because we used it all up, and we're not starting with any OH either. But we're going to lose some HCN we're going to lose some Cn- to make HCN and OH-. And at equilibrium, we have 0.048 minus X moles per liter of the conjugate base, X of the weak acid, and X of OH-. Oh, there's a throwback to questions 2 to 5. No wonder we do titrations at the end of the unit, am I right? Kb is the concentration of HCN times the concentration of OH- all over the concentration of Cn-. Remember, liquids do not play a role in equilibrium. And I knew to use Kb because it is the base that we are starting with. Unfortunately, we don't have Kb. But lucky for us, we can calculate it. 10 to the negative 14 divided by 6.2 times 10 to the negative 10. That calls for a calculator. 10 to the power of negative 14 divided by 6.2 times 10 to the power of negative 10. That gives me a Kb of 1.61 times 10 to the negative 5. All right, 1.61 times 10 to the negative 5 is X times X all over 0.048 minus X. When you do the rule of 100 or whatever, you'll find that that minus X is useless. Wait, is it? Let's actually test that. 0.048 divided by 1.61 times 10 to the negative 5. 2,981. Yeah, that's more than 100, more than 1,000. If your teacher set the threshold at 5,000, all of a sudden you have to use the quadratic equation to solve this. But that ain't us right now. We need to solve this, undo dividing by 0.048 by multiplying it on the other side. 1.61 times 10 to the negative 5 times 0.048 square rooted to get rid of the square on this x gives me an x of 8.79 times 10 to the negative 4, and that is my OH minus concentration. Thus, the pOH is the negative log of that number. You know what to do from here. Negative log of that answer gives me a pOH of 3.06, but the pH itself is 14 minus that. That gives me 10.94. A still basic pH. Well, that makes sense, because if I'm adding the same amount of weak acid and strong base, the base should win out in the end. The pH at equivalence here is almost 11. If you were to have seen the titration curve for this, you're starting with a weak acid, so you start in the acidic zone. When you add the base, your pH rises but then flattens because buffers are resistant to changes in pH. Then it starts to rise. Your equivalence point is up here at 11. Oof, well, 10.94, I guess. And then it will continue to rise a little bit until eventually you've just overwhelmed the whole solution with this NaOH. And like your pH can't rise any higher than whatever the pH of this is that you're adding. So like there's an asymptote here. It'll keep rising until it gets to that point, and then it's just going to call it a day, right? Okay, we got one more question here, and I'm only doing this in case your teacher expects you to deal with experimental results. Here, we have 1 gram of an unknown acid in 100 mils of water. 25 milliliters of that solution is titrated with some KOH. And you do that titration 3 times. They want to know the identity of the acid. One of the best ways to get the identity of the acid is either to know what the Ka or pKa is. I'm not sure we have the data to do that because we're only given information at equivalence here. The other way you can do it is to figure out the molecular mass in grams per mole. Now we were given grams, so it would be ideal to know how many moles that 1 gram represented. Now, the way that titrations work is that you have a little flask here that you put your acid into. Then you probably have a burette, which is one of those long tubes that you're holding up with a clamp. Then it's got this little thing called a stopcock at the end, and you twist it to let drops come out. And this burette is graduated so you can see exactly how many milliliters you started with and ended with. If you start at 0.02 and you end at 20.58, then you actually added 20.56 milliliters. I'm going to write that in as change. The difference in the milliliters is the total actual volume of the base that you added in milliliters. If you do it a second time, maybe you like refilled it a little bit up to 12.11, and then you titrated the same amount of sample, 32.69 minus your initial amount gives you 20.58 milliliters added that time. Then you fill it up another time, drip, 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 down to 34.66. That difference, when you subtract, is 20.34. How do you know which number to use? Well, the real answer here is you're supposed to average it. Add them together and then divide by how many samples you did. 20.56 plus 20.58 plus 20.34 divided by 3 gives me about 20.49 milliliters per sample. So each time I got 20.56, 20.58, perhaps I was overshooting the equivalence point a little. 20.34 may have undershot it a little, I don't know. On average, it seems to take about 20.49. Doing more and more and more trials is how you increase your accuracy. Okay, the point is, that's the number of milliliters of KOH that we needed to neutralize 1/4, 25 out of 100, of the original amount of unknown acid. I'll show you the math. The number of moles of KOH that we used up per trial is concentration of base times volume used. The concentration was 0.1 moles per liter. The volume was 0.02049. Again, I divided by 1,000 to convert milliliters to liters. That gives me 0.00249 moles. That's the number of moles of KOH per 25 milliliter sample of the acid solution. Now, if we assume that this acid had only one proton, then what that means is we had 0.002049 moles of acid per 25 milliliters of acid solution. And the real question is, how much HA in moles would there have been for 100 milliliters of acid? Now you can use the dilution equation for that, C1V1 equals C2V2, which I'm sure you've heard of. Now I don't actually have C's here, concentrations the same way, so it might be unintuitive. What matters to me is that if I have 0.002049 moles for every 25 milliliters, how many moles did I have per 100 milliliters? See, that's kind of like an equivalent fraction. In order to solve for that number of moles there, I undo dividing by 100 and times by 100 on the other side. 0.002049 times 100 divided by 25. Now please note that you might have been able to do that in your head. 25 is exactly 1/4 of 100. So if this represents 1/4 of the total number of moles of acid, you just times by 4 to get the actual number of moles per of acid. 0.008196 moles of HA represented that full 1 gram that was dissolved in 100 milliliters of water. The molecular mass or molar mass of the acid is mass divided by moles. 1.0 grams divided by the 0.008196 moles that it represented. 1 divided by that gives me 122.01 grams per mole. Now your job would be to figure out what chemical actually has that molar mass. I don't exactly know, but I can probably Google it right now quickly on my computer. Yeah, this is how we're finishing the video. Watch this. Google.com. Molar mass 122 acid. I'm just going to type that in. Oh, it gave me a result. It says here benzoic acid. Fun. Now, there's no way to prove that it's actually benzoic acid. Oxalic acid also came up. But, I don't know, you got to take your best guess, right? Whichever one your teacher gave you on a list. I don't know, your teacher can't really expect you to come up with a molecular formula from a molar mass unless it's some tiny amount. Benzoic acid was C6H5COOH. Yeah, that sounds to me like it weighs about 122, but that's not the point. The point is, you can get the molar mass of the acid by figuring out how many moles of base you required to neutralize some amount of that acid. And you can do it all in a lab by doing a titration a bunch of times, averaging your results, using that as the volume of base, and getting your number of moles of base at equivalence with that calculation. All right, well, that's actually the end of the package. Congratulations on finishing it with me. That was, I guess, 101 minutes of nothing but acid-based practice. I hope you found it useful. If you made it this far, shoot me a message in the comments. I always love seeing that I helped people, and it motivates me to make more stuff like this. By the way, I always take requests. You got a unit test coming up? I will make you a mega video. Just ask. I'm a good guy, and I'm sure you are a good person too. Take care, and best of luck.